So in this video, I will be showing you how to create this very cool halftone effect inside Substance Designer only using a single pixel processor. And of course, some very good looking input image to halftone the effect. We're going to build this together now step by step, because just showing you the final graph is maybe what you're looking for if you're just about to do the halftone effect, but I rather explain how we get there. So let me create a new pixel processor here. And again, use my input image here as an input image on the pixel processor. So what I usually do when I'm working in pixel processing is to always go into the output format and set it from 16-bit or whatever your graph is set to 32-bit, just to be sure that whenever we're dealing with some math or ranges outside of the 0 to 1 range, that we actually can inspect these values right here, right? I'm also going to set this to grayscale because, I mean, we could do this with color actually, but let's keep it with grayscale for now. And now I'm jumping into the pixel processor. So what we need first is a position grab. So whenever we are resampling images or manipulating images, we need some kind of coordinates to sample that image from. So if I now just take the sample gray here and use my position, which is, by the way, a float 2, just to remember X and Y. And I set this to the output node, then I get the original image back again. But we want to have this very, you could say dot matrix, this grid of dots that is appearing over the image here. So what we need to do first here is to create some kind of scaling to our UVs, because we want to repeat a certain image over that whole area a few times. So one way to do that would be to use a scalar multiplication, because to scale UVs, you basically just need to multiply them. And we need a scalar here because multiplying a float 2 with a float 1 isn't going to work particularly. So if we are going to use a regular multiply, we would have to convert this to a float 2 as well. Which you could do, but let's start with let's say 50. Multiply this, and for preview purposes, I'm trying to always showcase this in the output. So if I do this now, we can see we multiplied the image over itself 50 times in both axes. So we have a lot of repetitions here. But we are not really interested in sampling the image a lot of times, but we are interested in sampling a certain shape, like these dots, these shapes, which are going to represent our image later on. So we're going to make a little bit of space here. And the first thing I'm going to do is to use 2 swizzles, which actually are just nodes that help us to separate certain vectors or certain parameters from a certain vector. So we got X and Y here because we got position coordinates in X and Y. And by swizzling these, we can separate them. Which is now nothing you can really inspect too well because we scaled the UVs. So scaling them back reveals 0 to 1 in X, and doing the same here reveals 0 to 1 in Y. If we scale this by 50, you're going to not see much anymore, but just up here, 1/50 of the whole resolution up here. And you can see here when I'm inspecting these values that they are now ranging to 5, 6, 7, 8 and more. And this is also why we're going to set the whole pixel processor to 32-bit. Because if we're not doing this, you can see when I'm inspecting this now, we're always going to see just 1, because it's the values are there, but we cannot inspect them. So let's keep this to 32-bit. Go in here again. And the next thing we're going to do is to use a fractional on both of these axes. And let me quickly showcase this. So what the fractional node does is it only returns the fractional part of a scalar, or the fractional part of whatever input number we have here. So if I go back here and I inspect this, where my mouse is sitting, we have a value of 36, you can see here around. And the fractional part is only giving us back what is behind that comma. So we are actually at 36.26. So the fractional part is going to say, okay, we're at 0.26 here. And since we scaled our UVs beforehand, this is going to repeat 50 times across that axis. And it does the same thing vice versa on the Y, naturally. And what we're going to do now is to recombine this into a float 2. It's a little hacky to do that. We could also create a, I don't know, is there a fractional for... Yeah, there is a fractional vector too, but I think that's a custom one of me. And if I'm going to plug this in now into that graph, it's probably going to tell me there are missing dependencies or something like that. So we're not going to do that. But naturally on Designer, you only have fractional parts for a single scalar. So you have to swizzle them in X and Y, do the fractional part, and then recombine them to a float 2, which is again our position, right? The next thing we're going to do is to subtract 0.5 from these vectors. And the reason to do that is because if you're inspecting our fractional part here, we again have 0 to 1 values ranging, which is not exactly what we want to do because, well, it would be easier if I explain what this minus 0.5 is doing. So the minus 0.5 is basically shifting that UV chords by 0.5 in each direction, which means that it's not starting on 0 right at the top here, but it's 0 on the center. Let me quickly swizzle that again to display what it means. Yeah, so this is before we subtract, and this is after we subtract. And you can see that we are now like having 0 right at the center here. Always inspect these values here. We have 0 right at the center. We have negative values here, of course, because we're subtracting 0.5 from anything lower than 0.5, so we're getting in negative values. But that's not of concern. It's important that we like mark this center position here. So this is now like our pivot point, you would say, in 3D modeling. And we do this for both axes. So if I switch this over to Y, you're going to see that the same effect is applying here. And then to get rid of these negative values, we're going to use an absolute. And I should have kept the swizzle node here. So inspecting this will now reintroduce, like it's basically flipping what we did before. And we have a gradient that is like peaking at, you could say 1. In this case, it's 0.5 in the center. And it's 1 at the outer part. So basically we just have a mask that shows us where our center point is. And this is also again on the y-axis. So, but why are we doing all this? So we are doing these operations because we want to create procedural circles or disk shapes. And to do that, we can make use of a length function, which calculates the length from 1 point or from 2 points to each other. And if I quickly display this, you're going to see that we are turning from a float 2 to a float 1. If I'm now inspecting this, you're going to see that from our center point, or our center points, let me quickly choose point X here. We're now calculating the difference or the length to the other points. And because we're doing this for like X and Y in both axes, we're going to basically introduce a grid which has like the lowest distance like right on the crosses and the biggest distance at the center point. So this is a way to create like circles. We could also like do this with our base UVs, like no multiplication. So we're going to calculate the distance from the outer point to that center that we centered by using by subtracting 0.5, right? But we're doing this like 50 times because we need some more points than these, okay? So the next part, and this is like where we are already starting to like basically finish this effect, is to use a step function. And a step function basically gives you a binary mask based on the first input and then like a scalar value on the second input, which basically tells us how far are we actually stepping into that gradient. And since we have like a gradient from 0 ranging to, what is this, like 0.75? I mean, we could arrange these values again. So we're actually from 0 to 0.1, from 0 to 1. But in here, we actually just want to like mask this for now. And you can see like if I'm slowly increasing this, we're starting to see like binary dots. So this stepping function basically helps us to shape the size of these, which is cool. So we got our dot matrix, but in order to make this a halftone effect, we need to scale these points according to our input image. So wherever we have like a black input, we want those points to be like very small or non-visible. And at the same time, for anything that's white, we basically want them to be as big as possible. Or, I mean, we could range that again. We can actually range that. But generally speaking, we want that to be the case. So here comes our sampling in hand. So to make things easier, I'm going to just grab my position here and not recycle it. So we have another node down here. And I'm going to, again, sample my input image. And this input image contains all the data that we need to basically allow the stepping function to have a certain size, right? So if I would be really cheap here, I could just use this as my stepping x function instead of a float. And we are kind of already there, right? So this is already giving us some kind of good result, but it's a little noisy. Like it doesn't really look like circular. We are messing here with a few values. So to get that in a better range, we're not directly sampling from the input image, but we're using the input image to drive another input value for that step function. And to do that, we're simply going to use a lerp function, which lerps based on an input between two values. So we can like fix the values that we want to sample there to some other values. So for example, we're going to use 0 for, like, we don't want to see any circles for dark areas, which is going to be our input A. And then we're also going to, let's say, I don't know, 0.65 for the biggest circles. So again, this input image here, this year, drives a blending function between this value and this value. So if we now plug this in here, we're starting to see like a little bit more diversity on what we're sampling here. But it's still not enough for me. So what I want to do is to make sure that points or that any input that is like darker than a certain value is set to 0 automatically. So I don't get any like of these noisy points in here, even though my input image is actually kind of black. Like I don't see a lot of difference in these values here, but they're still appearing to be some circles. And I'm going to do that with an if statement. So if, and we need like some condition to fulfill, if any of these values, like any of the values we sample here at our UVs, is lower than, for example, 0.2. So anything that has a grayscale value that is lower than 0.2, then I want to resample this and just hard code it to 0. And if that's not the case, I'm just going to like reroute my original values here. And now I plug this in and you can see like now this mask is like very, very strong and it's partially already cutting in here. Right, and with that, there's only like one more effect that I want to introduce because I personally think it just looks better. And for this, we need another lerp function. And we're also going to sample our input image again. And what we're going to do now is to multiply our like stepping function, like our final, let's say final input, with a different scalar, like that. And then we're going to lerp between the stepped image that we have here, our actual input image, and this is based on this factor here. And what did I do wrong here? Oh yeah, not the stepping function, right? So I took the length here. So what we're going to do with that is that this parameter now controls how much of the original color is bleeding through all of these halftone points. So if we set this to 0, you can see that this is all binary. It's either black or white. And if you want to increase some depth, yeah, you can increase this value, and this is going to reintroduce a little bit of the original color in here. Right, and there is one thing that I noticed while I was recording this is that it's like very noisy in these points here, which is actually a very artistic and cool side effect that I didn't plan on having initially. But the reason for that is that right now we are sampling our input image at like 4K in a 2K graph, and it's having like each point samples more pixels than it should actually. So our grid of 50 by 50 points here, or disk shapes, excuse me, is actually sampling like an area of, I don't know, like maybe 50 to something points at the same time. So this is going to get a little bit noisy because if we are zooming on the input image, you see there's a lot of things happening here. There are a few ways to mitigate this. One way would be to introduce a blur grayscale right before we plug this into our pixel processor. Oops, that's the wrong input. Which fixes a few things, but you're going to notice that we still have this wobbly blobs. And again, I think that's actually a really, really cool side effect of this halftone effect. But let's fix this now just to showcase you why this is happening. So as I said before, our UVs are basically sampling now multiple pixels at the same time. So what we need to do down here, which is like our mask that helps to control the disk size, we need to set that to the same resolution as our disk grid. So each circle is actually just sampling one particular average grayscale value to pick a size from. We can do that by multiplying this with... so first of all, we have to scale the UVs the same. In this case, however, I will be doing a vector flow 2 out of this, so I can use a regular multiplication. Then we have to floor these values. And let me quickly picture this again here. What the flooring does is, again, please look at these values here. These are your debugger. We're basically setting all these values to the lower integer part. So these are now fixed steps. There's no floating point numbers after the comma. It's only like 1, 2, 3, 4, and so on. Right, let me quickly move this a little bit over because we need one more operation. And after we floored this, we again divide these new values by our original resolution. So let me quickly switch this up here so it's a little bit clearer. Like that, yeah. So we're going to divide this by our original resolution, which was 50 in both directions. And if I now apply this, or I preview again the x-coordinate, you're going to see that we have the same gradient that we did before, but right now we are having like very stepped parts of that gradient. And if you inspect these numbers, you're going to see like 0.2 gradual increase over these values. Like there's no in-between more. We're just cutting off these values by this math operation. Right, so what that will change is basically, if I plug this in here now, we're having like a pixelation effect. You're going to notice like a small jump. So let's quickly recap this. Like all the pixels are shifting downwards a little bit. And that's again because we're like not sampling from the center, but we're rather sampling from like either the start, like on the upper left corner or a lower left corner of a pixel. So to do that, we could again, let me quickly copy this, subtract 0.5 from this to sample like the center region. Oh, what is happening here? Oh, wrong. We have to add 0.5. My bad. Yeah, and this is going to put them back into like the correct position. So before and after. So now it's all set. Yeah, and as I said before, doing this will eventually average all the pixels into that specific grid. So now we have just one singular value for the same scale disk. And if I output this now again, you're going to see like we have perfectly rounded disk shapes. Right, so let me introduce back a little bit of the original grayscale values, which, by the way, same issue now. we shouldn't use this, but we should rather use this, because this is already the like pixelated, or yeah, the pixelated input. So no need of the original input, unless, of course, unless you want it to have that effect. But we want to lerp between the actual stepped function and our like pixel grid based on a mask that is made from the step function, so we don't see any grayscale values in these black areas in between here. And I think with doing this, we can actually increase it a little bit more, and this introduces like a very cool effect. So what we can do now is using this parameter as our scale for the whole resolution. So the more we add here, the more points are going to be scattered across our grid, which will reveal more resolution sooner or later. It's going to fall apart at some point because the circles are going to be too small or too big. So you can see they're already merging into each other and starting like to blend somehow. But from a distance, it still looks cool. Let's get back to 50 real quick. And with these two parameters, you can basically control the upper and the lower size. So I can also increase this to a lot more, which is starting to look like Lego actually. So I think you want to keep this down to like just a little bit so it's still circles. And you can also increase like the lower end. And this is going to override the mask that we did before here, right? So because we are only using this to lerp between two different values. So if on this side the lower value is already set to higher than 0, we are going to always see points here. Which again, maybe it's whatever you want, but it's good to have this control here. And this value is going to effectively cut out more of the image more and more and more. So you basically increase the contrast. You could chain the same if else again with values higher than a certain threshold. So you're going to cut down on the brighter values. But I think this is good enough actually.